Okay, guys, welcome to the new year, new calendar year, 2016. Let's start off with a little series and sequences, chapter 6 from the textbook. Really straightforward stuff this class. Let me just move some. Oh, I don't know what I'm doing. Okay, so we're looking at series and sequences. We'll look at sequences first, then series later on. So first up, we're looking at patterns here. So how do we get this pattern? What are the next couple numbers? 3, 6, 9, 12, 15. We're going to add 3 each time, 18, and then 21. Okay, let's look down further. If we look at this here, each of these is called a term in the sequence. So this first term is t for term, and 1 is equal to 3. T2 is equal to 6. So just some nomenclature, I guess. T1 means term number 1, and the value of term number 1 is the value of the first term, which is 3. So these are in order. So you can't go, it's not like the numbers are like this, and you go, oh, T1 and, which one's which or whatever, okay? They have to be in order. There's T1, T2, T3, T4, et cetera, et cetera. So those are terms. This one here is a term, if it keeps going and going and going, this is infinite term, or infinite series, okay? It goes on forever. There's nothing stopping it. Real life series, for example, if we had something like this, I think the example we use is, so if we said something like, for example, count the years in this decade. Well, at the end of the decade, you're done, right? You're all done, and that's called a finite series. When you look at the data that you look at, if I have 3, if I plotted this, the first term is 3, the second term is 6, the next term is 9. You look at this. First of all, it might be linear, which is one thing. But the other thing you look at here is there's no, we're not drawing a line here. So when we were doing quadratics and linear stuff, we were drawing lines, and then we were talking about how the domain is x is a real number, and we're looking at real numbers. Well, here we're not looking at real numbers. We're looking at natural numbers or the counting numbers. So there's no line here. There's nothing in between here. The first term is 3. The second term is 6. There's no 1.1 term, 1.6 term. There's nothing in between here. So we can't connect these with a line, and we call this discrete data. Okay. What was over here is continuous data. Okay, if it's connected with a line, but any data that is plotted, and when it's plotted, it's a series of points that aren't connected with a line, are called discrete data. Okay, that's about it really for this unit. The only thing, we look at things like this, and if you want to come up with some terms, so let's just do this one right here. I want to come up with the next 4 terms. So I go T1 is equal to 5. So Tn is this. That's the nth term, the general term. This is called an explicit formula. Okay, so explicit formula is the formula for Tn. You'll see the next unit, not everything's like that. The next section, not everything's like that, but in this case it is. So T1, here at Tn is this. I put a 1 for the n, I put a 1 for the n. So anywhere I saw an n, I put a 1. 5 to the power of 1 is 5, subtract 1 is 4. So the first term is 4. The second term is going to be 5 squared minus 1, which is 24. And then you keep going. Okay, T3, T4, T5. Besides that, from the note, the only other thing is here, that's straightforward. Number 5 here. Let's look at this for a second. I have the series 5, 7, 12, 17, 22, and you look at this right away and you say, I'm adding 5. I'm adding 5. I'm adding 5. If I said, what's the 5th term? You would add 5. You get 27. If I say, plot this, go ahead and plot this. No, what's going on here? Plot this. If I had the first term, the second term, and I'm going up, I think I did this, space 5, space 10, space 15, space 20. I was going to plot this. 1 was 5. 1 was what? 7. 2 was 12. 3, the third number is what? 17. Okay, and you look at this. You can't connect with a line. Okay, but let's pretend we could. We want to come up with the explicit formula. This is a linear relationship. Ways to prove it is you look at first differences. Okay, they're all 5. First differences are the same. It's linear. The other thing you look at, you can say to yourself, hold up on that for a second. So I have a linear relationship like this. A linear relationship in the old days is y equals mx plus b, and b was our y-intercept, and m was our rate of change. So we call this the rate of change. We also call it the slope. You may call it delta y over delta x. Okay, it's also the first difference. All these things are the same, and they're all m. So what your m is your slope. And if you look at this, you're going up 5 over 1. So you have a slope of 5. You can also use the points to figure out the slope, but the slope itself is 5. The other thing you look at is this. First difference is 5. Okay, but also if you go way back up to this, 7, 12, when I asked you originally, how do you get these numbers? Forget about slopes and lines and that. You said add 5, add 5. And if you're always adding the same thing, that is your slope, and you also know that it's linear. You have a linear relationship when you're adding the same thing because you have the same first difference. Okay, it's adding, same difference. The difference each time is the same. In this case, 5. So when I look at my equation, y equals mx plus b, my m is 5. I think I've shown that a bunch of times, and then I have x, and now I need my y-intercept. So I look here and I go, y-intercept. There's no y-intercept here. That would have to be over here where x is 0, right? The equivalent of x, which is n. So there's no point here, but let's see if we can work backwards here. If I had 0, so my fifth term was 27. If I had the 0th term, I don't know, that's not even a thing, but if I did, if this is 7 bigger, then this is 7 smaller. Or sorry, this is 5 bigger. I'm sorry. If this is 5 bigger, then this is 5 smaller. I go from 12 to 7, subtract 5. So if I did have a 0th term, which I'm making up right now, that would be 2. So if I was to plot something here, that would be 2. So my y-intercept would be 2. So I make it y is equal to 5x plus 2. That's my equation. If I did have a line, now I said don't connect these and don't, but if I did connect them, I'd have something like this, and that'd be the line y equals 5x plus 2. Now, we're not using x's, we're not using y's, and we don't have a line, but we can use that same information to come up with an equation set up like this, where I want Tn, so an explicit formula. So instead of y, I use T of n, and T of n, and instead of x, I use n. So it's 5n plus 2, and I'm done. Okay, so here's your first difference, or your rate of change, or your slope, or whatever. Here is the y-intercept, or the term that would come before the first time you see. Okay, first term you see. There's T1, T2. If there was a term here, what would it be? And that's your B. Okay, this is way too crazy, so we're not going to do that. If you want to look at this, this is on page 357 of your textbook. There's an example here for that. It's interesting, but I'm not going to hold you to it. So that's that. That's how you come up with explicit formulas. Okay. If I had another formula, let's come up with this one, for example. If I had this, 3, 9, 15. Actually, let's even make it more fun. Let's go back. So that's minus 6, so minus 3. I look at this and I want to come up with a formula for this. Okay. Pretend it's a line. What would my formula be here? Well, if this is T1, T2, T3, T4, okay, my slope each time I'm going up by 6. Okay, and then I want to know what my y-intercept be. So if I graph this, I'm down here. Okay, my first term T1 is minus 3. The second term is 3. Then 9 and 15. What would this be if I had a T0? Well, it's 6 less, which would be minus 9. So that goes right there. That would hit here if I had a line. If hit at minus 9. There's how I set it up. Except I don't write it like that. I write it like this. Okay, I get rid of y and I replace with t at n, and then I replace x with n. And I'm done. Okay, so hopefully that makes sense. That's the explicit formula. Okay, I don't know if I said that. That's the explicit formula. And you're asked to do that, I think, in question 4 of your homework. Okay, great job. Take care.